I came across the speculation that maybe our universe is a simulation, a fake.
What is real and what is not real? Even though you might feel you know the answer, the James Webb Space Telescope has waded into the debate and its findings are shocking. We exist inside a simulation. How did we end up in a simulation, and how did the JWST reveal this? Stay tuned as we dive deep into the James Webb Space Telescope's discovery that shocks the entire space industry. We are living in a simulation. Have you seen the Matrix movies? The films depict a dystopian future where humans are enslaved by machines and live in a virtual reality called the Matrix. The movie suggests that we live in a simulation by showing that the Matrix can be manipulated by hackers, glitches, and anomalies, and that some people can escape it and see the true reality. This raises the question of what is real and what is not. It also raises the question of how to determine what is real and what is not. Scientists use empirical evidence to decide what is true, which is data that can be witnessed and measured using the senses or instruments. They also employ the scientific method, which is a methodical process of developing ideas, testing them through experiments, and amending them based on the results. The scientific method assists scientists in avoiding biases and errors in their reasoning and in determining the best explanations for natural events. And scientists also compare their findings to those of other researchers who are working on the same or similar areas. And they use peer review, which is a procedure in which researchers evaluate and critique one another's work before publishing it in scientific journals. Peer review ensures that published research is credible, reliable, and unique. Scientists also convey their findings to the general public and policymakers who can use scientific information to make educated decisions. One thing, however, that scientists avoid doing is professing to have absolute knowledge or definitive answers regarding reality. They recognize that their knowledge is speculative and prone to change as new evidence and methods become available. They also acknowledge that there are boundaries to what science can study, such as philosophical or ethical issues that are not quantifiable or measurable. Scientists are curious about the natural world and are open-minded about it, but they also utilize critical thinking and skepticism to examine claims and evidence. And this uncertainty certainly applies to the universe as well. Is anything real? Do we exist in a simulation? The concept and dread that reality is not what it appears to be can be traced back thousands of years to the Chinese philosopher Zhuangzi's butterfly dream. Philosopher Nick Bostrom made the prospect seem inevitable in 2003. He contended that future civilizations could have access to massive quantities of computing power, allowing them to run an almost unlimitless number of simulations. If that is the case, the possibility of us existing in one of the billions of historical simulations appears to be almost certain, or else post-human society will have no motivation to simulate histories or will never achieve technological competence. In the decades since, the theory has been advanced by Elon Musk and Neil deGrasse Tyson. Silicon Valley millionaires have apparently sought to conduct their own investigations as well, with two going so far as to secretly engage scientists to work on breaking us out of the simulation. But fortunately, or perhaps sadly, there is nothing we can do to get out. That is, as far as we are currently aware. This is the real world, since our cosmos cannot be simulated, and mathematicians have known this for years because they have been attempting to do so. On the surface, the case for simulation appears compelling. Pong, a simple 2 pixels and a rectangle, was the pinnacle of technology 40 years ago. Now we have photorealistic graphics, deepfakes, and virtual reality at our fingertips. Future civilizations appear destined to advance even further and to recreate scenarios from their distant past. However, even before getting into the scientific concerns, this argument runs into a few roadblocks, such as the premise that such a future civilization could ever exist, or that the species would wish to replicate humans, Earth, or even this galaxy. It's as probable as the presence of God or the multiverse, absolutely possible, but scientifically useless. This argument is also influenced by our understanding of physics, space, and time. When Isaac Newton discovered the laws of motion over 300 years ago, philosophers compared it to one of the most exquisite scientific advancements humanity had made: clocks. The universe's rhythm, both on Earth and in the stars, was so exact that the connection seemed clear. The parallel was utilized by theologian William Paley in his arguments for God's existence. Finding a watch among the grass, he argued, proves the existence of a watchmaker, just as finding God in the world implies the existence of God. Every indication of contrivance, every manifestation of design which existed in the watch exists in the works of nature, with the difference on the side of nature of being greater or more, and that to a degree which exceeds all computation. However, neither Newton nor Paley had to deal with the complexities of today's cosmos, which has revealed itself to have such weird eccentricities as superposition, string theory, quantum physics, and dark matter. The idea of a mechanized universe gradually faded away as we learned more about reality. And in 50 or 100 years, a simulated universe will appear just as childish as the clockwork universe. Scientists have spent many years trying to comprehend the origins of the cosmos, either by examining the extremely huge or the very small. Paley inferred the existence of the watchmaker to explain the origin of life, whereas simulation proponents consider the possibility of simulators. The Big Bang and the cosmic background radiation it left behind are the best explanations for the universe in physics. However, evidence that this has been mimicked is scarce. We glance at the subatomic instead of the stars. So where would we find the gears of the cosmos if it were a clock? Where would we look for pixels if the cosmos were a simulation? However, evidence that this has been mimicked is scarce. We glance at the subatomic instead of the stars. So where would we find the gears of the cosmos if it were a clock? Where would we look for pixels if the cosmos were a simulation? Both gears and pixels have the property of being discrete. In mathematics, this indicates that they are separated from one another, with each part unique from the others, much like Lego bricks are fixed to their base. A massive Lego sphere may appear flawlessly smooth from a distance, but closer inspection reveals the individual blocks. As far as we can tell, the cosmos is not like Lego or Grand Theft Auto. People do not resurrect. Trains are not hat-wearing NPCs. On the surface, it appears that everything works, but video game characters are not performing the necessary research. Now, it is feasible that the universe has a pixel, but existing scientific understanding is insufficient to investigate it. The Planck length is one of the smallest scales we know. This is the length of the cosmos after the first 1,043 seconds of the Big Bang as it expanded. Unfortunately, the Planck length is 15 orders of magnitude smaller than what we can currently test with a Large Hadron Collider, and would still not be enough to establish the universe is a simulation, only that it's discrete. And even so, the universe poses another barrier, the Nielsen-Ninomiya theorem. This is a no-go theorem, an impossibility in which condition can occur in the universe but not in simulations, and it has to do with hands. Consider staring in the mirror and waving to yourself. Your reflection raises its opposing arm in imitation of you. This is an example of chirality, which comes from the Greek word for hand. A chiral object is one that can be distinguished from its mirror image. A left hand cannot be overlaid on a right hand. This property can be found in big molecules, such as those found in fruit. Although an orange and a lemon peel appear to be very different in color, taste, and fragrance, both peels contain limonene molecules that are reversed counterparts of each other. The same may be said of mint and caraway, both of which are reflections of the molecule carvone, as well as the thalidomide medication, which is hazardous in its mirror image and has resulted in thousands of children being born with serious birth problems. Chien-Shiung Wu discovered chirality while watching atoms die in December 1956. These were radioactive cobalt-60 atoms which emit an electron when they decay to form nickel-60. Now, whether in the real world or the mirror world, the electrons should have decayed in a random direction according to their spin. Instead, they showed a desire for the decay direction. Imagine staring in the mirror and holding up a newspaper, but instead of seeing the letters inverted, the words are fully readable, as if someone from another universe was mirroring you. Wu discovered this on a subatomic scale. And simulating the laws of physics in a computer is where these two issues, chirality and discretization, come to clash. In the real world, if space is periodic, a quantum physics term that roughly translates to a circle, momentum is discrete, made up of different pieces. In contrast, physics states that if space is discrete, as in a simulation, momentum is a circle. If you maintain enough momentum, you will eventually return to your starting point. This is similar to playing Pac-Man and reaching the right-hand edge of the maze before returning to the left-hand edge. Pac-Man eats a discrete point in the simulation for each pill he consumes, and if Pac-Man were a chiral particle, he could only move one way along the width of the maze in one dimension. Pac-Man expends a lot of energy to reach the right-hand edge, but when he returns from there, all of that energy is gone. This is impossible in physics because Pac-Man has moved from right to left despite only being allowed to travel in one direction. Today's simulations handle this by constructing a mirror Pac-Man that moves the other way, left to right, and mathematically is the same Pac-Man. This would translate to electrons from cobalt-60 atoms moving in the opposite way in the real world, but as these do not exist, the universe as we know it is genuine. However, there is one caveat to all of this. Scientists do mimic the cosmos. There are some physics principles where the mirror universe has no effect. Magnetism, electricity, gravity, and the strong nuclear force that holds quarks together are all unaware of the concept of parity. These forces function the same in the mirror, blind to particle spin. Scientists have been trying to mimic chiral particles for 20 years, but in the end, what they do is they don't. They get around it by simulating both hands of particles and then just throw away the other one when looking at the data. Simulation enthusiasts will try to get around this by using more sophisticated scenarios. There is a distinction between being able to simulate the universe completely at the level of fundamental physics on the one hand and being able to simulate the perceptions and experiences of a human being or all human beings on the other. The latter is only relevant for the simulation argument. According to Bostrom, such a simulation may rely on procedural creation to only generate what scientists are looking at the time. The ground beneath your feet merely seems solid. The soil does not appear until you dig it. The chiral boson exists only when scientists try to quantify it. And Neil deGrasse Tyson has proposed that the speed of light is the limit of travel because if we traveled any faster, our mystery overlords would be unable to replicate our cosmos quickly enough. This is known as the light cone. However, the universe is intricate according to Professor Berman, and nature appears to know everything. Because of the curvature of light around gravity, astronomers have observed the same supernova explode 4 times in 4 distinct locations, and general relativity puts a spanner in the works of causal connection. This, he claims, makes it difficult to imitate sections of the cosmos without necessarily modeling the entire thing. At the moment, our understanding of science is somewhere between reality and the simulation hypothesis. Occam's razor, which states that the simplest answer is always the best, remains a difficult nut to crack. Now, one question raised by the simulation hypothesis is whether the Big Bang was the start of the simulation we are living in, or if it was a part of it. In other words, did the simulation's inventor or programmer start it from a state of singularity and let it evolve according to physics principles, or did they mimic the Big Bang and its aftermath as part of their design? Here are several examples. The simulation started with the Big Bang. This situation may have been inspired by simplicity and curiosity. The inventor or programmer may have wished to develop a realistic simulation of their own universe, or a variation thereof, and observe how it evolved through time. They may have launched the simulation from a singularity and let it run according to the physical principles they knew or assumed. This concept is also compatible with some philosophical or theological beliefs that interpret the Big Bang as a creation event. The simulation included the Big Bang. This scenario could be justified by complexity and control. The developer or programmer may have sought to create a more detailed and customized simulation of their own universe, or a different one to see how it would react under different conditions. As part of their design, they may have replicated the Big Bang and its aftermath and adjusted some parameters or initial conditions to produce alternate outcomes. This scenario is also compatible with some philosophical or religious beliefs that interpret the Big Bang as a manifestation of divine will or intelligence. And this is where the James Webb Space Telescope comes in. The JWST has been researching the Big Bang by observing the cosmic microwave background CMB, which is the universe's oldest light, emitted approximately 380,000 years after the Big Bang. The CMB contains information on the universe's beginnings and evolution, including its geometry, expansion rate, matter content, and primordial fluctuations. JWST has been measuring the CMB spectrum with unparalleled accuracy and sensitivity, as well as looking for probable deviations from the mainstream cosmological model via its mid-infrared instrument MIRI. JWST has also been researching the Big Bang by looking for the first light sources that appeared after the cosmic dark ages, which lasted hundreds of millions of years after the Big Bang. The first stars were huge and short-lived, producing heavy elements and ultraviolet light, while the first galaxies were small and feeble, hosting supermassive black holes. JWST's near-infrared camera NIRCam and near-infrared spectrograph NIRSpec have been used to detect and characterize these sources, as well as to determine their distances and redshifts. And the JWST has also been researching the Big Bang by observing the era of reionization, which happened when the first light sources ionized the vast majority of hydrogen atoms in the intergalactic medium, bringing the cosmic dark ages to an end. The reionization epoch left a mark on the CMB and influenced the birth and evolution of galaxies. JWST has been investigating the reionization history and its impact on cosmic structures with its near-infrared imager and slitless spectrograph NIRIS and MIRI instruments. JWST has also been seeing the cosmic dawn, which occurred when the earliest stars and galaxies generated enough molecular hydrogen to cool and collapse into more complicated formations. The cosmic dawn signaled the change from a simple to a complex universe, and it influenced the following history of star creation. JWST has been searching for molecular hydrogen emission from these structures and studying their physical properties using its NIRCam, NIRSpec, NIRIS, and MIRI instruments. Another scientist proposing we live in a simulation is Melvin Watson, a physicist at the University of Portsmouth, and he has devised a method for determining whether we are living in a computer simulation. His theory is predicted on the concept that physical reality is fundamentally made up of bits of information from which space, time, and matter emerge. He also assumes that any simulation has a minimum size or resolution below which it cannot be further subdivided. Watson contends that the smallest components of the universe, basic particles, may include information about the possible programming language. He proposes that by measuring the attributes of these particles, such as their mass and charge, we can find patterns or anomalies that expose the simulation's underlying code. He compares it to zooming in on a computer image until we can see the individual pixels. And Watson created a mathematical model that describes how the information content of elementary particles can change depending on whether or not they are part of a simulation. He also proposed a test of his idea using existing particle accelerators, such as CERN's Large Hadron Collider. He argues that his experiment can differentiate between three scenarios. 1. We are not in a simulation and physical reality is not affected by information. 2. We are living in a simulation in which information completely determines physical reality. 3. We are living in a simulation and physical reality is influenced by information. Watson's idea is one of several attempts to empirically test the simulation hypothesis. Other approaches include looking for flaws or contradictions in physical laws, as well as breaches of Bell's inequalities, which are mathematical constraints that every local realistic theory must meet. Watson's idea, however, is unusual in that it concentrates on the information content of elementary particles as a possible simulation signature.